If I met you and you're also named Adam, then that's... Sorry if I forgot you, but I thought I was the only one. Oh, okay. Okay, so the title of my talk is Dear God, What Am I Doing? Concurrency and Parallel Processing. And I came up with the idea for this talk because once upon a time I was a very scared man of my computer. I had only written sequential programs, and I had to do some work that required me to make a new thread and start forking and things that I had no clue what was happening and scared me. So if this talk is for you. Like if you have experience writing parallel programs, you're comfortable working with that, you have written programs with Celluloid, or you have written your own web server like Puma or Unicorn, this is probably going to be kind of boring for you. But the talk should be educational for the people like me. So how many of you guys have opened threads and forked stuff before? OK. Well, this might be not you, because this was me when I started doing it. And it just, for me, it went horribly wrong. But it was a great learning experience. So before we can get into talking about all the different ways we can approach these problems, we need to take a brief detour into machine architecture. And computers are probably one of the most complex things that us humans ever built. But when you get down to it, we have a bright light, and we're not at the end of the tunnel yet. There's still 40 minutes to go. So we have threads and processes. And this, from a high level, it's not so complicated, but it is very complex. And we can break this system down into the following diagram. So there we go. We have a hamster, which is like a thread, and we have the wheel. Keynote is horrible with GIFs, apparently. And the wheel is the process. OK, well, if I could go back. OK, wow. So we have threads and we have processes. Processes are composed of threads, and you can scale these out to do many things. So when you want your computer to go faster, what you really want to do is just copy and have this, and have all the hamsters running at the same time. But unfortunately, what usually happens is something like this. And you can get back on and try again, and it just keeps happening. But so I had a lot of things I wanted to talk about during this talk, and the topic is so large, I had to choose what I wanted to talk about, and ended up with a wide range of many different things. So if you have no experience, this should get you started. If you have some experience, you should shore up what you already know. So the talk isn't for people like this who know everything, apparently. They've made their own languages. They have all this fancy stuff. They don't need it. So now that we're done with memes, we can start talking about actual important stuff. So the question we all face, especially with Ruby, is how can we make it faster? We had Charles talking today about the JVM, and yes, it's important to make it faster. Ruby is generally fast enough, but it can be faster. So I'm a car guy. I like to work on cars and make them go faster, because when you're in the driver's seat and you hit the gas, it feels good when you go fast. So when we need our cars to go faster, we usually throw some boost at the thing. If you don't know what this is a turbo, also two of them, so twin turbos. And what they do is they compress air and shove more air into the engine, giving you a more powerful explosion and propelling your car forward. So the real thing that we're going to do with our computer is just make it do multiple things at once. Like, we already do this all the time. Like, how many of you chat, browse the internet, and listen to music and do all those different things at the same time? Like, that's me. I do that all the time. So in order to get this job done, we have 3 primitives. We have processes and threads and fibers. Processes are separate from everything else. They have their own memory space and are scheduled by the kernel. Threads are inside processes, share the same memory space as the process and the other threads, and they're scheduled by the kernel. Oops. And then we also have fibers. I'm not going to really talk about fibers too much because they're just like threads, except for you have control over when they start and when they stop. So the kernel is the one who's basically deciding when your code gets run. And processes or threads may block depending on what's happening. The most common blocking operation is I/O. And apparently the Node.js people won't shut up about this because non-blocking I/O is the best thing ever. It is nice, but it's OK. So the real thing that we have to worry about when we're working with threads and processes is the different semantics in the different interpreters. So the big thing is MRI versus essentially everything else. We have JRuby and Rubinius, which handle threads completely differently than MRI. And this has changed drastically between 1.8 and 1.9. In Ruby 1.8, there were green threads, which was just inside the VM, not actually backed by a native thread, which puts limitations on them. And at Ruby 1.9, we have actual native threads. So every thread you instantiate in Ruby is backed by a native thread object. So the first thing that we can look at is threads. And it's the easiest way to get going if you just need to do some more things at once. So we're going to look at some threads. Threads are below processes. And we can just instantiate a new thread very easily. So you can instantiate as many threads as you want to, but you don't have control over when they run. So there is a problem with this code. Who knows what it is? Exactly. So this is like the first thing that happened to me is I made a thread, and then I run it on my editor, and nothing happens, and I just scratch my head because I don't know what's happening. So the problem is that you don't wait for the thread to finish. So now you have a main thread and some other threads. And if you're delegating work out to the child threads, the parent thread has to wait for the main, or the parent thread has to wait for the child threads to finish. Yeah, tongue twister. So if you have an array, you can call join and wait for them to finish. Now, the other thing with threads is that when you run this, you'll get something like this. And you run it over and over again, the numbers are going to change. They will become out of order. You can't control when the threads are running, generally. Now, what makes threads easy to work with is they have a shared memory space. So here's a simple example of, well, shared memory. So we have 2 threads, one thread that is calculating interest on a shared bank account balance, and one that's just printing it out. And this works because we can access the variables in the same place. So there's also a problem with this code. The problem is now we need locks. We have one variable that needs to be protected, so only one thing can access it at the same time. And you can do this by including a mutex and wrapping it in a block. And the lock will block until it becomes available, so you can ensure exclusive access to certain parts of your code. And this is pretty much what you have to do with threads. And it would be great if you didn't have to use locks, but you may. We'll talk about a little bit later what we can do to avoid using locks. So blocking. The major operation, or the major thing that's going to cause your threads or your processes to block is I/O. And Ruby 1.9 does a lot of things to make handling blocking better. So I/O blocks, and Ruby will allow you to do parallel I/O. If multiple threads are waiting for I/O, Ruby will select one that's closest or ready to finish and run that one. So that's pretty much how it goes with threads. So now we have processes. And processes are awesome because you can pretty much do everything in a thread that you can do with a process, but you can spawn off as many as you want, depending on how much your machine can handle. And you instantiate a new process, usually with fork, and off you go. So now we are going to talk about processes, and they are, here's a simple example of a processes. So just the same as before with the threads, except for, well, the same thing. You also need to lock here. And the main difference with processes is memory is not shared. So you have to go through more hoops to make all this work. And that involves IPC or inter-process communication, which can become very complicated. So if you were to run this program, you would see stuff like this. And well, you need to do something. You need to take care of that. The Ruby cannot take care of that for you. So fibers, you can compose your applications also with fibers, but it's a little more work, and they have a very small heap space. So you have to be careful what you do with fibers. So now we can make some things faster. So one common thing is you have a lot of operations, or like you have a set of operations and you want to parallelize them. So for the next part of the talk, I'm going to use like this example. So we want to query the first 100 pages of Google search results for the Ruby keyword. And we want to do that as fast as possible. But this is an interesting example because it's going to have I/O in it, which will be blocking, which highlights a problem in MRI. So the two approaches for this is to use threads or to use processes. So the first example is multithreaded. And I did this like a million times. I'm sure people have done it before, where you would just loop. And it works, but you can do it faster. And it took like 45 seconds or so to do this on my Wi-Fi connection. But, well, it's sequential. It's going to take time. But like, you have more resources at your disposal. You just have to know how to take care of them. So I have cores. I can make some more threads. So I start to think, OK, I have 4 cores in my machine. I can instantiate 4 threads, and they can just pull stuff off a queue. The queue here is from the Ruby standard library. It is partially blocking. So we can run this code and time it, and now it only takes 8 seconds. So that's pretty big. So the difference is 40, like over 40 or less than 10. So then I think, OK, great. I'll just use more threads. So I open up my editor, make a command line argument, and say, OK, I want to do 5, 10, 15, 20, whatever number of threads I can think of. So then I run this a few times and kind of see what happens. And coming from my previous experience where I had 1 thread to 4 threads, I expected the performance to be somewhat linear. However, that's not the case. As you can see, with 10 and with 9, it's not really even worth it, because there's overhead in switching between threads. And if you can spend more time switching between threads than doing the work you would be doing. So this is because context switching and mostly because of I/O. And so the next example is about, well, math. So I don't know about you, but I'm kind of interested in Bitcoin, and they do hashing and can be intense, and you need to do thousands and thousands and thousands of hashes. Or if you're more malicious, you can do password cracking. So this is just an example. This does not involve any I/O. This is just plain computation. So create a queue and then have a dictionary and run through all those examples in different threads. And I would like this to go as fast as it possibly can. So I want to instantiate just a ton of threads and then run them all at once, and then use a queue to share the data between them. So I get my script ready, and then I just go to my biggest computer I can possibly find and start to run this code. And it's just slow. Like, it just doesn't work. And now we enter a space that is unfortunate, is we have to talk about the global interpreter lock. And the global interpreter lock is a part of MRI that says that only one thread can be executing Ruby code at the same time. So in this case, I have all my threads, and they're just calling out to SHA. Only one of them can happen at once. So that's unfortunate. This is what makes like true parallel programming, impossible to do with MRI. This is just not allowed. So thankfully, we have JRuby and Rubinius. And it's great. This really is great news for all of us, because we can begin to do the things that other languages can do, and we can have the speed. Yeah, so MRI has the GIL, JRuby and Rubinius don't. And when it started to do work with JRuby, this is what it felt like. But really, we can thank him for that. The simple fact of the matter is that JRuby and Rubinius are simply faster when you need to do this sort of work. There's a new web server, Puma, that just came out, as been mentioned a few times in some of the other talks. And it's fast, because recommended you run on JRuby, and you can take advantage of these different things. So we talked about multi-threading, and now we can talk about multiprocess. Now, multiprocess is quite powerful. There are a few prominent gems that use multiprocess models, mainly Unicorn, which starts your app and then forks off a number of workers to handle requests. There's also the Zeus gem, which uses forks to fork your Rails app during a certain stage of the boot process, so you don't have to boot again. So now we could do the same thing, but with multiple processes. So this is a very simplified example, which generates the pages, generates a list of queues, like a set of pages to pass to each process, and the process goes off and gets all them. And this is reasonably fast, and it works. Now, once you fork off your process, you can also instantiate threads inside your process. And this is where it starts to get kind of fun, but also kind of crazy, because you have to take all of this into account. Oh, man. So in this example, I have a process which is instantiating a number of threads. And this is the fastest you could possibly do it. And there is something is missing in this example that you'd have to do in the real world. There's no notion of inter-process communication. This example works easily because the queue is passed in via a block variable, and you would usually have to do some synchronization if these processes are going to be running independently, but that's not the case in this example. But this is the fastest you can possibly do it, and it does work out really well. So, these simple examples are simple. They work, and they demonstrate the concepts, but they kind of blow up when you get to more complex situations. Because if you have a long-running process, you have to synchronize it, it has to talk to other processes, and you have global state, which you may need locks, or hopefully you can deal with immutable data, which is one way to get around that. And there's a problem in all those examples, and it's a slight quirk in the Ruby standard library queue. So all the examples use this code. And this is an example of how I screwed myself over and just messed up. So we have a queue object that has all the things the threads need to process. And while the queue has some stuff, OK, then pop one off. However, the empty call is non-blocking, and pop is blocking. So given a sufficient number of pages, or a number of iterations in this loop, this can deadlock. Because what will happen is the queue, the empty call, will just execute immediately. So when the queue actually is empty, it will return true. But then another process or another thread can hit that at the same time and also return true. And then pop will return an item in one case and then nothing in the other. Now, it goes into deadlock because pop waits for the queue to have something. Now, deadlock is a situation in which two competing actions are waiting for the other to finish, and thus neither ever does. And I sat there running this code on my computer and thinking, OK, what's happening? I don't understand how this could possibly deadlock. There's no I/O. There's nothing. I don't know what's happening. And then I read the code for the queue, and oh, OK, empty is non-blocking. Great. So the simple fix for this is to override our queue class in the examples and to change it to wrap empty also. Instead of just calling while queue.empty, just say while value equals queue.pop, and that will work. So those are simple examples. But now we can move on to easier concurrent Ruby programs. How many people here have used Celluoid? OK. How many people have used Sidekick by chance? OK, more people have used Sidekick. Sidekick is built on Celluloid and built on top of the actor model. So each actor is an object running in its own thread, and Celluloid handles communication with mailboxes. So it's written by Tony Acieri, and he's a really cool guy. He also won the Ruby Hero Award last year. It handles pooling, supervising, messaging, and pretty much everything related to handling objects in multiple threads. And it makes writing concurrent code easy as writing sequential code. And according to the README, you should never be able to make it deadlock, because of how it's structured internally. So it's pretty easy to use. This is just an example of using the worker pool functionality. This is the same way that Sidekick uses Celluoid. So you can instantiate a pool of workers, and you can pass in, if you want, a number of threads. Like we have worker.pool that uses the number of cores by default. However, you could pass in like 5, 25, 100, or whatever. And then we can have our worker just go out and simply fetch the page. This is not necessarily as fast as using multiple processes and using multiple threads. However, that code is much easier to understand, which is a big win. And then, of course, all this still comes into play with the global interpreter lock. So on the README for Celluloid, it essentially says, this will work. However, you should definitely be using JRuby or Rubinius. But there really is like so much more to all of this, because you have threads and you have processes, but there's also different approaches. Like you can also use things like event machine and go evented, similar to the way Node does it. But when you start to go down this road, you need to do a lot of different things, like mostly monitoring. Like if you have your like child threads or child processes, you have to make sure that they're up, especially if they're doing stuff, and that adds overhead and complexity to your program. But the biggest thing is handling global state with locks or immutable objects. How many people went to the immutable Ruby talk earlier? Yeah, so that's definitely one way to get around this. And yeah, so I mean, you have like your database, you have all that stuff needs to be protected, and usually like Postgres will have something built in to handle this case, but if you're doing your own objects, you need to protect them or make them immutable somehow. So how can we make Ruby faster? Well, you can commit to MRI. You can work with JRuby. You can work with Evan and Brian on Rubinius, or with Charles, and I'm not sure who else is on the core team, but work with JRuby and make that faster. Now, I am actually somewhat embarrassed because I managed to go through my slide deck much, much faster than I practiced. And so, unfortunately, that's it. But I'd be happy to answer some questions or talk about some other stuff if other people had things they wanted to hear about. Yeah.
So an example you said in celluloid, it would look at number of cores.
Yes.
And use that in many threads. What's the advantage of that if we're still kind of inside of a single core bound process?
Well, isn't that up to the scheduler to decide?
What was the question?
So the question was, what's the benefit of using multiple threads when you're still bound to a single core, right?
No, it was in celluloid, you said it returns by default the pool size equal to the number of cores.
Correct.
In your hardware, but you can't really use those cores from a single process, right? Is that correct?
Well,
you can only use one core.
Well, that's not really our problem, because that's the operating system is going to schedule those threads for us. Right. And yeah, so if it's programmed, if the kernel can support it, then it will run it on multiple cores. Like I took, just for those examples, I mean, on my MacBook Air, I have, quote, 8 No, yeah, 4 cores, two physical cores and 4 virtual cores. And running those examples will max out your computer. We'll run it, yeah, well, it will use them juggling, right? But of course, if you run it on JRuby, then it will use them all at the same time. Like in the hashing example, it will utilize all the cores. Yeah. Anybody else? Oh yeah, over there.
You basically just said that interprocess communication is difficult. Can you talk a bit about how you might approach it?
Well, it's very use case specific. I mean, one thing you might do is use some sort of messaging system to communicate. Because it really depends what the processes are doing. If the processes are long-lived, then you probably want some sort of message bus. So Unicorn uses a socket to communicate back and forth, right? Which is pretty much the easiest way, because you don't have shared memory. You have to have something else to do that for you. And you can also use, I think, DRB to handle some stuff as well. But it just depends on the use case and what you want to pass in between. You can use the built-in Unix socket library to talk back and forth if you want to. Yes?
Does Celluloid or any extension to it have anything to make it easier to have active and distributed across processes or across machines?
Did everybody hear the question? No. Is there any extension to Celluloid to make it easier to have distributed actors across multiple machines? That was the question, yeah? Not to my knowledge. Oh yeah, okay, yeah, forgot, sorry. Yeah, so Celluloid actually has a lot of other things built in as well. There is Celluloid I/O and decell. So decell for distributed Celluloid, and Celluloid I/O, which is asynchronous I/O for Celluloid actors. But I haven't used decell before. Yeah. I believe if you use Celluloid I/O, it has its own wrapper around that stuff.
OK, well, thank you very much, Adam.
You're welcome.